So in this lecture, we'll be discussing Fermi level in N-type semiconductors. Okay, so it will be Fermi level in N-type semiconductors. We know that in N-type semiconductors, the electron concentration it is nearly equal to number of donor atoms. Okay, electron concentration is nearly equal to number of donor atoms. Therefore, as we know that n is also equal to, that is number of electrons, it is equal to Nc e to the power minus e Ec minus E of F divided by Kt. We have discussed in our this thing in our previous lecture. Whereas Ec is the energy of conduction band, Ef is the energy of Fermi energy, it is Fermi energy, and K is Boltzmann's constant, and T is temperature in Kelvin. And therefore, we can say that Nc e to the power minus Ec minus E of F divided by K of T, it is equal to Nd. Okay, if we substitute equation A or equation B in our equation A, we will obtain equation C. And if we rearrange these terms, then we can obtain that Nc by Nd will be equal to e to the power Ec minus E of F divided by Kt. So rearranging, further, we have, if we take ln on both sides of this equation, then we will have on left hand side, we will have natural ln of Nc by Nd will be equal to ln and exponential will be cancelled out. Then we'll be left with Ec minus E of F divided by Kt. This is what we will be left with. Okay. If we further rearrange them, we can finally see that we will have Ec minus E of F will be equal to Kt times ln of N divided by, this is basically Nc, not N. Okay. So it is Nc divided by Nd. Nc divided by Nd. And further simplifying it, we will be able to find that Fermi energy in N-type semiconductors, Fermi energy level in N-type semiconductor, it will be equal to energy of the conduction band minus Kt ln of Nc by Nd. Okay, this is the relationship that will give us the Fermi energy level in N-type semiconductors. Fermi energy level in N-type semiconductors. Fermi energy. Okay. Okay. And we know that in this equation, where Nd is nothing but it is donor or it is doping concentration, N-type doping concentration. Okay, it is donor or N-type doping concentration. So we can conclude that in N-type semiconductors, in N-type semiconductors, Farzan is here. Farzan, फैजान है यहाँ पे रोल नंबर 72. Can you hear me? फैजान. What about 65? Atif? 69 Suhail? 22 Nashra?
Yes, sir.
Okay, so let me remove those students first who are not responding to my call. It means that they are not present. 75 is here. All
Yes,
right,
sir.
75. Okay, 73 is here. 73. 73. Okay, 73 is removed now. 72 Faizan. 72. 75, please turn off your mic. 72. 72 is here.
Yes, sir.
जी क्या पढ़ रहे थे हम?
Sir, and is equal to
69 is here.
yes, sir.
क्या पढ़ रहे थे बेटा हम?
सर डोपिंग कंसंट्रेशन के आप ये लिख रहे थे सर, ये जो फर्मी ये
Be attentive. Otherwise, I'll remove you from the group. Okay, you should not be uh, joining the class if you are not available, if you are not free or interested. What about 68? 68 is here.
यस
Roll
सर
number 6. क्या पढ़ रहे थे बेटा हम? Okay, I'll ask randomly questions from now onwards. If somebody will not respond, I'll immediately remove him from the meeting. Okay. So we can say that in N-type semiconductors, we are basically discussing Fermi energy level in N-type semiconductor. That is, how can we calculate Fermi energy level in N-type semiconductors? Okay, so that was the topic.
माइनस था ना
Yes, minus
सर यस सर माइनस ई सी माइनस ई एफ
minus EC minus EF.
यस सर
माइनस
माइनस
EC
कॉमन है
कैसे
ना
आएगा?
शायद
नहीं
फिर
ये
ऊपर दिखाया
माइनस
ना
जो
सर
था
आप
यहाँ पे, हाँ ऊपर जो माइनस था बेसिकली, क्योंकि क्योंकि हमने एन सी बाई एन डी निकाला, ठीक है, एन सी बाई एन डी। अगर आप यहाँ देखेंगे इस इक्वेशन को, अगर हम लेंगे एन सी बाई एन डी विल बी इक्वल टू 1 डिवाइडेड बाई ई टू द पावर माइनस ई सी माइनस ई एफ डिवाइडेड बाई के टी। अब सिंस इट इज इन डिनोमिनेटर, अब ये जो डिनोमिनेटर में है, सो दिस माइनस साइन विल बिकम पॉजिटिव। ओके, क्योंकि ये डिनोमिनेटर में आया। अब अगर हम ये स्टेप देखेंगे, it will be nc by nd will be equal to 1 upon e to the power something, okay, e to the power minus something. Since 1 upon e to the power negative is in denominator, when it will be written as a numerator, in the numerator, then it will become positive, तब ये
यस
positive
सर
बन जाएगा। समझ में आया?
यस सर यस सर
Okay, all right, ठीक है। So while as in n-type semiconductor, we can say that, we can conclude that Fermi energy or Fermi level is a function of, it is a function of first, yes. So EF is the Fermi energy, okay? EF is the Fermi energy. It directly depends on temperature. It directly depends upon KT. So it is, Fermi energy is a direct function, or it is a function of first is temperature. So as temperature changes, the Fermi energy level also changes. Okay. Second, it is also a function of ln of Nc by Nd. Nc by Nd is nothing but it is doping concentration. Okay. Nd is nothing but the doping concentration. So we can say that Fermi energy in N-type semiconductor, it is a function of temperature and doping concentration, doping concentration. Okay, so let us discuss these two effects. Case one would be, uh, let the temperature is equal to 0 Kelvin. When the temperature is equal to 0 Kelvin, then equation D, using in equation D, we have, what will we obtain? We will obtain that we'll have E of F will be equal to, yes, if we substitute T equal to 0 in equation D, what will be E of F equal to, Munazza? 67. What will be E of F equal to? Munazza beta? Okay.
Yes, sir.
What will be E of F equal to?
We are substituting the E of F is equal to EC. T is 0. KT will be 0.
Yes, it is equal to EC. Very good. It is equal to EC. Okay.
Minus.
So E
Yes,
of
sir.
F will be equal to EC. That means that at 0 Kelvin, okay, that means that Fermi energy or Fermi level in N type, I'll write it down. Fermi level in N type semiconductor at T equal to 0 Kelvin coincides. It coincides with EC. Okay, it coincides with EC. That means that N-type semiconductor at 0 Kelvin, uh, this this Fermi energy coincides with DC, or we can say N-type semiconductor at 0 Kelvin is insulator, because no charge carrier or concentration, no charge carrier concentration is present in the EC. Okay, we can represent this in this way. If this is conduction band and this is your valence band, we know that this is your E of V, and we know that this is your E of C, and your this will be the next one. Okay, the blue one, or let me change the color to maybe to orange, or to yellow. So this yellow one is basically now E of F. So E of F here coincides, or it overlaps with E of C, but we know at 0 Kelvin there will be no electrons or free charge carriers present in the conduction band. It means that N-type semiconductor at 0 Kelvin, 0 Kelvin is an insulator. Okay, it is an insulator because no charge carrier will be present. And since at 0 Kelvin charge concentration will be 0, therefore sigma is also 0. Sigma is the conductivity. Okay, sigma is conductivity. So because no charge carrier will be present in conduction band, sigma will be equal to 0, and we can say that it will be working as an insulator, working as insulator. All right. Now case second, if temperature is not equal to 0. Case second, if T is equal to 300 Kelvin, it is not equal to 0 now. So when T is equal to 300 Kelvin, then Fermi energy can be given as EC minus, EC minus KT, then ln of NC by ND. Here, temperature T is equal to 300 Kelvin. It is equal to 300 Kelvin. Or if we substitute this 300 Kelvin, it will be EF will be equal to EC minus, K into 300 Kelvin into ln of NC by ND. It will be something. Okay, it will be something. We can write it down. It will be something. It will be a non-zero quantity. And we know that if something is reduced or if something is subtracted from EC, if something is subtracted from EC, then EF will be, it will be less than EC. It will be less than EC. Or we can say that EF is below EC. So at 300 Kelvin, the level of Fermi energy or Fermi level will be below EC. It will not be coinciding EC. Okay, it will not be coinciding. So we can write it down in n-type semiconductor, n-type semiconductor at 300 Kelvin, Fermi energy level is existing. It is existing just below the donor energy level. Just below the donor energy level. Okay, just below the donor energy level or conduction level, just below the donor energy level or EC conduction band energy. Okay, so I'll draw this in this way. The diagram could be drawn in this way. Suppose this is your conduction band. This is our valence band. We know that this is E of V, and we know that this is E of C. Okay, and somewhere here we know that donor energy level is near conduction band. We have already discussed it. Therefore, the Fermi energy here will be just below the donor energy level. So EF is not coinciding EC, rather it is below ED or it is below EC. So EF is just below ED or it is just below at EC. Please remember that once we were discussing intrinsic concentration, we said that EF is at the middle of uh, EC and EV. We said that Fermi energy level in intrinsic semiconductor is halfway of the EG. We have already derived that. Now see, we can show this or we can represent this in this diagram also. Suppose you have this diagram and I'll extrapolate these lines. This will be your E of C level and this will be your E of V. And we know that in n-type semiconductors, the concentration of electron is very high in conduction band. The concentration of electron is very high in conduction band. So this is electron concentration and hole concentration, because holes are minority in concentration. They are minority carriers. We know that minority carrier concentration in a majority carrier in an extrinsic semiconductor is very less, while as majority carrier concentration is very high. So electrons are majority carrier concentration and they are existing in conduction band. Therefore, their concentration will be very high, while as the hole concentration that is represented by smaller area, this is hole concentration, it will be very small. And in between them will be somewhere Fermi energy, but it is near EC. It is near EC. So Fermi energy is near EC, or just below the donor level energy level, just below the donor energy level. So this is ED, for example, E of D. Is it fine? ये समझ में आ रहा है आपको? What about roll number 2, Hasib?
Yes, sir. आ रहा है.
Okay. Uh, what about 54? 54
Yes,
को
sir.
समझ. Roll number 8. Roll number 8.
Yes, sir.
Okay. What about 13? 13?
Yes, sir.
कोई सवाल तो नहीं है बेटा?
No, sir.
Okay. All right. Now see, if we draw a combined energy diagram showing Fermi level concentration of holes and concentration of electrons, this is how we can draw it. Okay, this is how we can draw it, a combined diagram. A combined diagram showing the concentration of holes as well as concentration of electrons. So say for example this is somewhere valence band and this is somewhere conduction band. Okay, then this is how we will draw it. The portion here which is shaded with red will determine us the electron concentration, and the portion here which is shaded in valence band using red color, it shows us the whole concentration. And this level will be donor energy level E of D, and yellow one will be Fermi energy level E of F. And this is the center of the forbidden energy gap. So you can observe that EF is just near the conduction band. Okay. So in this diagram, which was the previous diagram, these are basically density of states in conduction band or and valence band. This is density of states. When it is valence band, it means holes. Okay, density of states in valence band, and this is density of states in conduction band. Okay, but at 300 Kelvin. This is not at 0 Kelvin. This is at 300 Kelvin. Okay. Now this was the second case when temperature was 300 Kelvin. The third case would be case 3 would be when temperature increases beyond 300. Okay, when temperature increases, when temperature increases, when temperature increases, when temperature increases. Now see here, as temperature increases, we know that it means that NC will also increase. NC will also increase, and we assume that NC is still greater than ND. Okay, NC is still greater than NC. Then we can see from the equation, from equation D. Okay, from equation D we can say, from equation D we can say that EC minus E of F will be still greater than 0, or we can say that EC is greater than E of F. EC is greater than E of F, meaning that Fermi level is lesser than EC. Okay, it is still lesser than EC. So in N-type semiconductor, as temperature increases, EF moves away from conduction band, that is Fermi level. As temperature will increase, the minority carrier concentration will also increase. We have already discussed this in class. And at very high temperatures, we have discussed it that extrinsic semiconductor, it is converted into intrinsic semiconductor. Okay, at very high temperatures, extrinsic semiconductor is converted into intrinsic semiconductor. Since the E of F Fermi energy was near the conduction band, when temperature increases, it will move towards the center, because in intrinsic semiconductor, the Fermi energy is at the center. Okay, Fermi energy is at center. So we can say then in N-type semiconductor, as temperature increases, we'll write it down, in N-type semiconductor, as temperature increases, Fermi energy moves away from conduction band, or Fermi energy E of F moves towards center, towards center, okay, of the energy gap, वो इसलिए होता है because I said that as temperature increases, extrinsic semiconductor, the minority carrier concentration increases so much, extrinsic semiconductor is converted into intrinsic semiconductor. And because of that, we say then the number of minority carriers is nearly equal to majority carriers. Therefore, as we have already discussed, the Fermi energy in intrinsic semiconductor is at the center. Therefore, this Fermi energy, it moves towards the center. It moves away from EC towards the center of energy gap. So this is EG, forbidden energy gap. रोल नंबर 13 को समझ 16 को ये समझ में आया?
यस सर।
ओके, कोई सवाल तो नहीं है?
नहीं सर, फिलहाल नहीं है।
व्हाट अबाउट 20 को समझ में आया?
Yes, sir.
किसी को कोई क्वेश्चन तो नहीं है इसके बारे में? Okay, now see, moving towards center, moving of forbidden this Fermi energy, moving of Fermi energy level towards the center, moving of Fermi energy level towards center, towards center, it means that conductivity will, what will happen to conductivity, roll number 13, if Fermi energy level will move towards the center?
Sir,
What is the conductivity in
Conductive-
intrinsic semiconductor?
intrinsic 0 सर कम डिक्रीज हो जाएगी.
Decrease हो जाएगी, बिल्कुल ठीक. I will write it this in this way. Moving of EF towards the center would mean that extrinsic semiconductor tends to become intrinsic semiconductor. Therefore, sigma will decrease. Okay, therefore sigma will decrease, conductivity will decrease, and moving of Fermi energy level away from center would mean sigma increases. Okay, so we can say then, hence in n-type semiconductor, as temperature increases, sigma also decreases. Okay, sigma decreases, conductivity decreases with temperature, conductivity decreases with temperature. That is the first case. We had already discussed that Curie temperature and all those things in our class. Now the second thing would be what will happen as the doping is increased in n-type semiconductor. So as doping increases, what will happen to Nd? Nd is number of dopant atoms, okay, or donor atoms. It will also increase. Okay, so if Nd increases, therefore let us assume that Nd is much higher than Nc. Okay, Nc. Therefore we can say then Ec minus Ef, or I'll write it down like this using equation using equation D. We can conclude that Ec minus E of F is less than 0. Okay, or Ec is less than E of F. Ec is less than E of F. It means that if doping concentration increases, please note it down. This is your conduction band. This is your valence band. And your Fermi energy level is just near your conduction band. This is your Fermi energy level in n-type semiconductor. And this is your EC, energy of conduction band. This is your E of V. Now, as doping concentration increases, what will happen? Fermi energy becomes much higher than EC. It means that this Fermi energy, instead of moving towards the center, it will move towards the conduction band. Okay? It will move towards the conduction band, because for EF to be greater than EC, the situation should be like this. This is conduction band. If this is E of C, then E of F should be somewhere here. E of F should be somewhere here. So E of F moves towards EC and it merges inside the conduction band. It merges inside the conduction band. So we can conclude that as doping concentration increases, as doping is increased in n-type semiconductor, Fermi energy level, it moves into conduction band, And if EF moves away from the center of the energy gap, then it means that sigma also increases, because moving away from the center would mean increasing the sigma. So we can say that hence, with increase in doping, sigma increases in n-type semiconductor. Okay, we have already discussed these things, but I'm just uh, trying to give another logical reason why that happens. Okay, now see upward shift of Fermi energy level is denoted by a positive sign. So when Fermi energy is shifted into the conduction band, we say that we have obtained a highly doped n-type semiconductor, okay, or highly degenerated n-type semiconductor. So I'll write down here this line. When E of F moves into conduction band, comma, a highly doped n-type semiconductor, or highly degenerate n-type semiconductor is obtained. Okay, it is obtained. So then we can say that sometimes it is asked in the question as, in a highly degenerated n-type semiconductor, the Fermi energy exists in. So the options might be given like in between EC and EV, near EC, just below EC, just above EV, or inside the conduction band. So we can say then in highly doped or in highly degenerated n-type semiconductors, EF is noted down. EF, which is the Fermi level, it exists within or in the conduction band. This is very important. Please remember it. तो कभी कभार ये गेट में भी एक बार पूछा गया था, in a highly doped n-type semiconductor or in a highly degenerated n-type semiconductor, the location of Fermi level energy is near the conduction band, near the valence band, and so other options. And one of the options inside the conduction band. So the answer was inside conduction band. Okay, so because it is like this, it always is inside the conduction band. Roll number 19, कोई सवाल तो नहीं है? Roll number 19. What about 22?
No, sir.
22.
No, sir.
समझ में आया?
जी सर.
नहीं आया समझ में?
सर आया समझ में.
Okay. Okay. What
सर आपने ये
about
बोला ना
23? हाँ बताओ.
Yes, sir.
Okay. हसीब बताइए.
सर आपने बोला in n type semiconductor temperature with increase in temperature conductivity decreases, but 0 to 300 Kelvin सर increase होता है ना, फिर decrease होता है.
हाँ वो तो उस वक्त होता है. This is a very high temperature. It is if you note it down, मैंने 300 तक अलग एक केस लिया. Then after 300 I took, it is very extremely high temperature. When the temperature is very very high, तब ऐसे होता है. ठीक है, वो हमने ऑलरेडी
Okay.
इसकी एक्सप्लेनेशन दी है जब हम क्यूरी टेम्परेचर डिस्कस कर रहे थे क्लास में फ्रॉम द ग्राफ. So in
Yes, sir.
context that wherever there is a violation, that graph still is valid and it is quite authentic. So this is
Okay.
general discussion. Okay, कोई और पूछना चाहता है? रोल नंबर 23 आपको समझ में आया बेटा?
जी सर, जी सर.
ओके, ठीक है. Okay, all right. Now, sometimes it is also, imperative to calculate the shift uh, of the Fermi energy level due to doping. Shift of the Fermi energy level, यानी कितना shift हो रहा है. So we can sometimes determine the shift in the position, shift in the position of Fermi energy level due to doping. Due to doping, what will be the shift, okay, or shift from intrinsic concentration. So the shift will be always given as because it is due to the concentration Nd. Shift is always given as Kt ln of Nd by Ni if you are measuring with respect to intrinsic semiconductor. Yani intrinsic semiconductor में the Fermi energy level is at the center, but in n type it is towards the conduction band. And if somebody will ask you how much it has been shifted from center to that position, then this is the shift you can calculate by this formula, and it will be always in electron volts क्योंकि जो shift होगा, forbidden energy gap is measured in electron volts, Fermi energy level is also measured in electron volts, so the shift will be always in electron volts. Okay, now we can discuss. We'll come towards the Fermi energy level in p-type semiconductors. Fermi, let us start from here. So we have already discussed Fermi energy level in n-type semiconductors. We'll discuss the Fermi energy level in p-type semiconductors. P-type semiconductors. Now in p-type semiconductors, we know that hole concentration is nearly equal to number of accepted atoms. Number of accepted atoms. Okay, hole concentration is nearly equal to number of accepted atoms. And we know that hole concentration is given by N of V e to the power minus EF minus EV divided by KT. Okay, if we use equation B, using equation B in A, we will be having that NV e to the power minus E of F minus EV divided by KT, it is equal to N of A. Okay, similarly, if we rearrange these terms, NV by N of A will be equal to E to the power E of F minus E of V divided by KT. Okay, and rearranging them further, we can have this combination EF minus E of V will be equal to KT ln of NV by NA. And finally, we can extract E of F from this equation. E of F, that is Fermi energy level, will be equal to EV plus KT ln of NV divided by N of A. This is, say, for example, the final equation C. So we can say that in p-type semiconductors, Fermi energy level is also function of temperature and function of doping concentration. So we can observe that in p-type semiconductors, Fermi energy level E of F is function of temperature, and doping concentration. Okay, because you have temperature term here and you have doping concentration also in the term. So similarly, we'll take three cases here. Case 1 will be at T equal to 0 Kelvin. At T equal to 0 Kelvin. Usman will tell us at T equal to 0
जी
Kelvin.
सर.
Usman is here, roll number 13.
Yes,
Yes.
sir.
Where will be what will
EF
be
is
E of
equal to
F
EV.
equal to?
EV.
EF will be equal to EV. So where will be EV? At the top of the band diagram?
At the top of valence band.
At the top of the valence band. What is EV?
Sir, energy of valence band. Maximum
How is
energy
it
of
measured?
valence band.
It is maximum energy of valence band. Yes, and
Yes, sir.
EC is the minimum energy of conduction band. So
जी sir.
when T is equal to 0 Kelvin, then it means that E of F it coincides with your EV. So this is EF, and using black lines it was E of V. Okay, E of V. So we can say that at 0 Kelvin, E of F coincides with EV, energy of valence band, okay, at 0 Kelvin. And since at T equal to 0 Kelvin, the carrier concentration is 0, therefore sigma is 0, and we know that P-type semiconductor will be working as insulator, okay. At 0 Kelvin, P-type semiconductor will be working as insulator because carrier concentration is 0, okay, carrier concentration is 0. Now see, the second case would be when the temperature will be greater than 0. Say for example, the temperature is 300 Kelvin, okay, 300 Kelvin. What will happen then? Then it will be E of F will be equal to EV plus, KT ln of NV by NA, where T is 300 Kelvin. Or we can say that in general, it will be equal to energy of valence band plus, because it is a non-zero term now, plus something, for example, plus some non-zero term, which means that E of F is having a higher value than E of V. Okay, EF is greater than EV. So we can draw this in our band diagram. If this is our conduction band and this is our valence band, this is our E of V, this is our E of C, and therefore E of F will be above valence band. This is, for example, center. So this is E of F in P-type semiconductors. Okay. And if we draw the diagram of density of states diagram, then this is how it can be drawn. So we can have one here, another line here, and we'll have this, say for example, somewhere here. So this is the center. So this is Fermi energy level in P-type semiconductor, and in P-type semiconductor, number of hole concentration or holes, it's very high. So we'll have hole concentration very high as compared to the electron concentration. So this is hole concentration, okay, at T equal to 300 Kelvin. And this is electron concentration, because in P-type semiconductor, electrons are minority carriers and the concentration will be very low. It will be small. Or in P-type semiconductor, we can say hole concentration is greater than electron concentration. Okay, so you can note it down that the energy level or Fermi energy level is just above the acceptor energy level. If this is E of A, E of A, it is just above the acceptor energy level, just above the acceptor energy level. We can show a combined diagram for this, a combined diagram. So we have these two diagrams. एक में हम energy level दिखाते हैं, Fermi energy levels. दूसरे में हम concentration of states, density of states दिखा रहे हैं. Okay, density of states. Now these two diagrams can be combined together in this way. These two diagrams can be combined suppose this is our conduction band, this is our valence band, then we can see that concentration of holes is much higher in the valence band and concentration of electrons is much lower in the conduction band. And this is the acceptor energy level or your Fermi energy level. This is the Fermi energy level. This is the center of the band diagram. Center of the band diagram. Okay. Is it fine? यहाँ तक कोई 21 यहाँ कोई क्वेश्चन तो नहीं है आपको? रोल नंबर 21.
No, sir.
What about 25? बेटा आपको कोई सवाल तो नहीं है?
No,
30, roll number 30. Roll number 30.
No, sir.
45.
No, sir.
53.
no, sir.
Okay. What about 64? 64.
No, sir.
Okay. All right. So the next case would be what will happen when the temperature will increase. Okay. Case third. As the temperature will increase, as temperature increases. So we know that E of F minus E of V, it is equal to KT, KT ln of NV by N of A. Okay, this is the equation. This is the equation. Now see, if temperature increases, as temperature T increases, what will happen then? NV also increases. Okay, NV also increases. NV also increases. And if NV increases, we can say then let NV is greater than N of D. Okay, N of D. Sorry, NV is greater than N of A, not ND, NA. Okay, here we have any number of acceptor atoms because it is p-type semiconductor. In that case, EF minus EV will be greater than 0. Okay, EF minus EV will not be equal to 0. It will be some positive quantity because if we substitute the values into this, it will be greater than 0. Or we can say EF is greater than EV. EF is greater than EV. So in p-type semiconductor, as temperature increases, we can say that Fermi energy level will move away from the valence energy level. Okay, because EF is greater than EV would mean if you have valence band here, तो आपकी valence energy यहाँ है E of V, so E of F is higher than this. E of F is higher than this. At 0 Kelvin, EF and EV was coinciding. But as temperature increases, then EF will move away from EV. Okay, it will move away from EV. Therefore, we can write down in p-type semiconductor, as temperature increases, as temperature increases, Fermi energy level moves away from moves away from valence band. Moves away from valence band. That is moving towards the center of the energy gap. So moving towards center of the energy gap would mean that sigma also decreases, okay, because moving towards center would mean it is tending to become an intrinsic semiconductor. So hence we can say sigma decreases with temperature. क्योंकि जब energy gap E Fermi energy it will move towards center. Please remember that it is trying to become an intrinsic semiconductor, and in an intrinsic semiconductor you have a very less conductivity. So in p-type semiconductor, the position of Fermi level for different temperatures is, will be different, and for a 0 Kelvin, it will be always coinciding with valence band. But as temperature will increase, this Fermi energy will try to move towards center. It will try to move towards center. Okay, it will always try to move towards center. And when it will move towards center, in that phenomenon, sigma will be always decreasing. Sigma will be always decreasing. Okay, sigma will be always decreasing. And at very high temperatures, at very high temperatures, we know that this will the Fermi energy level will go into the valence band. Okay, जैसे हमने कंडक्शन जैसे हमने n टाइप सेमीकंडक्टर में कहा था, तो उसी तरीके से यहाँ पे भी होता है. When you have very high temperature, then I will write it down. In a highly doped p-type semiconductor, or in a highly degenerated semiconductor, the Fermi energy level is existing in valence band, the way it was existing in conduction band in n-type semiconductor. Okay, it is existing in valence band, and we can represent that diagrammatically also. If this is, for example, if this is your conduction band and this is your valence band, we can say that Fermi energy is somewhere here, E of F. Okay, and this is, for example, acceptor energy level, which is near valence energy level. Okay, this is E of C. So such types of semiconductors, because they are highly doped, they will be represented as P plus semiconductors or P plus plus semiconductors. Okay, P plus semiconductors or P plus plus semiconductors. So this phenomena is because of doping. As doping increases, so when doping increases, हमने पीछे भी दो cases लिए थे. When temperature will increase, we said that conductivity will decrease, but as doping will increase, what will happen? Then p-type semiconductor will try to become a highly doped semiconductor, and in a highly doped semiconductor, the Fermi energy level will be in valence band if it is p-type semiconductor. And therefore here there will be a downward downward shift for a Fermi energy level. Okay, downward shift, which is denoted by a negative sign. And you can also measure shift here. जो मैंने वहाँ पे discuss किया था, I am trying to rush because I have already discussed this thing. You can also measure shift here. Shift in the energy level will be equal to kT ln of A. It is ln of Na divided by Ni, and it will be also in electron volts. Okay, so we will solve some questions. Is it okay? Roll number 62 कोई सवाल तो नहीं है बेटा? What about 13?
No, sir.
13? Okay.
No, sir.
16?
यस
16
सर,
को
यहाँ पे
समझ में
शायद
आया?
सर शायद -kT होता है यहाँ पे शिफ्ट में.
कहाँ पे?
इस वाले
हाँ,
शिफ्ट में।
तभी मैंने कहा शिफ्ट हम नेगेटिव लेते हैं, तभी मैंने कहा
यस
ना।
सर।
तो आई सेड दैट EF, I'll write it down here. EF, Fermi energy level, will shift downwards. Okay, and I said
ओके
that downward shift is taken as negative, or it is represented by negative sign. और जहां एन टाइप सेमीकंडक्टर में शिफ्ट अपवर्ड होता है तो वहां पॉजिटिव साइन से होगा। ठीक है, तो मैं यहाँ वो लिख दूंगा, इन N type semiconductor, let me write it clearly. In N type semiconductors, the shift for E of F is upwards, and upward shift is taken as positive. Okay, upward shift is taken as positive. तो यहाँ एक्चुअली माइनस साइन होगी बिकॉज डाउनवर्ड शिफ्ट इज टेकन एज नेगेटिव एंड अपवर्ड शिफ्ट इज टेकन एज पॉजिटिव. That is why you are saying that shift will be minus times. Okay. Anyway, what is shift basically? Shift is, how do we define shift? Although I have told you verbally also, but we can write it down that shift in general, it is measured as the level of Fermi energy, level of Fermi energy in, say, for example, p-type semiconductors minus the level of Fermi energy in intrinsic semiconductor. Okay, that is basically the shift. Now see, in intrinsic semiconductor it is at center. ठीक है, तो इसका वैल्यू होगा कहीं पे somewhere here. Say for example it is at the center. Okay, but in p-type semiconductor, this is conduction band, this is valence band. The Fermi energy is not at the center. So center is somewhere here, but it is just below, it's just above the valence band. So इसका value कम होगा. So when you will take a smaller value and you will decrease a larger value from that, that is why shift will be negative. तभी जाके आपको negative sign आती है. ठीक है, तो that is why we take downward shift as negative and upward shift as positive. So this is shift in p-type semiconductor. But if you are talking about shift in n-type semiconductor, this is how it will be measured. It will be Fermi energy level in n-type semiconductor minus Fermi energy level into intrinsic semiconductor. So here you know that in n-type semiconductors, Fermi energy is somewhere near the conduction band. Okay, it is somewhere here. So this is Fermi energy level. It is not at the center. Center value तो यहाँ है. But in intrinsic semiconductors, you have conduction band here and you have valence band here, but your Fermi energy is at center. Okay, EF of I, and this is EF of N. EF of N will have higher value as compared to EF of I. That is why the shift will be positive. ठीक है बेटा ये मुजम्मिल?
यस सर।
Okay, is it fine now?
यस सर।
So we can now measure the shift in the Fermi energy levels also. All right, then I think I'm done. So let us solve some questions. I'll ask students
Excuse me,
one by one. Yes, please.
Sir, I have a question. Sir,
Mm.
if as temperature increases, Fermi energy becomes greater than the valence band and the maximum energy in the valence band. वो
In which
उसके बाद
semiconductor you are talking about?
P-type,
P or
P-type,
N?
sir.
P type?
P-type. Yes,
Okay.
sir. Then how does it coincide with the valence band? अगर वो पहले उससे away जाती है, as temperature increases, Fermi level moves away from the valence energy.
See, first of all, you can explain the coincidence with the mathematical relation equation C. Okay? When you will insert T equal to 0, this entire term will be equal to 0. So EF will be equal to EV. Okay? EF will be equal to EV. That means whatever is EV, that is EF. or we can say that EF and EV coincides. But once the temperature increases, there will be some positive quantity that will be added to EV, because now this equation will become EF will be equal to EV plus some positive quantity. Okay, some positive term. So when something is added, a positive term is added to something. For example, you have, suppose EF is X and EV is 10. Okay. अगर यहाँ the next term will be 0, you know that x is equal to 10, it means EF is equal to EV. लेकिन अगर आप इसमें +1 करोगे apply, यानी you are adding some non-zero quantity, a positive quantity, it means that now it is becoming 10 plus something. 10 plus 1 is 11. Now EV was already 10, but when EF will become 11, it is above that, the level is above that, क्योंकि आपकी जो level होती है start, वो होगी असल में ऐसे. ठीक है, ये है आपके bands. तो आपकी रेफरेंस लेवल होगी समवेयर हियर. इफ दिस इज द रेफरेंस लेवल, then increasing value would mean here. So you will have always some value here, but whatever value will be at EG center, वो हमेशा EV से ज्यादा होगा. इसी तरीके से E of C का वैल्यू EG सेंटर से भी ज्यादा होगा. आपको समझ में आ रहा है ये?
Yes, sir.
ओके, कोई और सवाल है? Let us follow some questions. I'll ask students one by one, and I'll note down students who will not be responding back. Okay? Please write down a question. Write down a question. Okay. All right. The question is, in an N-type semiconductor. I'll write down here. Just let me try to check the questions. Okay. Okay. The question is like this example. The question is, in an N-type semiconductor, in an N-type semiconductor, the Fermi energy lies 0.3 electron volt below the conduction band. At 300 Kelvin. Okay, at 300 Kelvin. Now, the question says, if temperature is increased to 330 Kelvin, find the approximate new position of Fermi level. Find the approximate new position of Fermi level. Okay. Now see, in N-type semiconductor, we know that EC minus E of F, it is equal to K of T. Then it is ln of NC by ND. Okay. This is the equation. Okay. Since NC value is not given and cannot be found, the variation of NC will be the temperature, will neglect the variation of NC. No variations in NC with temperature will be neglected because NC is not given here. इसमें NC का ये नहीं दिया गया है. Therefore, we will neglect the variations of temperature on NC. ठीक है? We can directly say from this equation that is given here. So first we'll write down neglecting variations in NC due to temperature. Okay. Then we can find from equation 1, which is equation 1 here, we can say that EC is basically directly proportional to E of F. Okay, E of F. Because if we rearrange the equation 1, it will be EC will be equal to E of F plus something KT into something. Okay? It will be like this. So EC is directly proportional to E of F, and it is also directly proportional to temperature. It is directly proportional to temperature. And we know that the conduction band or the Fermi energy level was 0.3 electron volt below conduction energy level at 300 Kelvin. Okay, so we can write down like this. E of F was 0.3 electron volt, which is directly proportional to 300 Kelvin. Okay, 300 Kelvin. So this will be equation 1. Similarly, we can also say that EC minus E of F is also directly proportional to temperature. Okay, let us keep rest of the things as constant. Or we can say that EC minus E of F is directly proportional to 330. So this will be equation 2. Now see, we have two different equations, and we know that in the first equation we have some constant here, and in the second equation we will have a similar constant here also. Okay, so we'll have a similar constant here also. We can write down then or we can divide equation second by equation 1. We'll write down like this: dividing equation second by equation 1. This is an approximate way of calculating the things by neglecting certain variations. So we will have EC minus E of F divided by 0.3 electron volt. Then you will have here 330 divided by 300. Please calculate what is EC minus E of F. That means the new energy level. How much below is the new energy level below conduction band?
0.33 electron volts.
Yes, it is 0.33 electron volts. Write down another question. Another example is in an N-type semiconductor, the Fermi level lies 0.4 electron volt below the conduction band. If the concentration of donor atoms is doubled, we know that Fermi energy level also changes with the doping concentration. So if the concentration of donor atoms is double, find the new position of Fermi energy. New position of Fermi energy level. Okay. Assuming K into T will be equal to 0.03 electron volt. So KT, you have to assume it is equal to 0.03 electron volt. Now see, we know that ND is nearly equal to, it is given by NC e to the power minus EC minus E of F by KT. Okay, by KT. All right. Now see, we know EC minus EF. How much is Fermi level energy below conduction band? Yes, Usman.
Yes, sir.
How much is Fermi energy level below conduction band? It is 0.4 electron volt.
जी सर.
है ना? तो ऊपर
Yes,
ये
sir.
है. Sorry. So this value is also given. ठीक है? Please calculate.
0.4.
Please calculate what will be then. Okay, then we can say that ND will be nearly equal to NC into e to the power minus 0.4 electron volts, and KT का value दिया गया है, it is 0.03. Okay, this is equation 1. Now, in the second case, it says that the donor atom concentration has been doubled. Okay, donor atom concentration has been doubled. So ND will become twice ND now. Okay, ND will become twice ND. ND will become twice ND, and NC will be same. Then it asks that find what is the new position of Fermi energy level, that is EC minus E of F you have to calculate by KT is 0.03. So there are two equations and you can calculate now. Please divide them suitably and calculate what is EC minus E of F. So dividing
0.37 electron volt.
0.37 electron volt is the first answer. Okay, 0.37 electron volt. What is the next answer we will have?
0.379 electron volt.
Very good. 0.379. दोनों का ठीक है. ठीक है. So this is the correct answer. 0.379 electron volt is the correct answer. All right. Similarly, it is also given, and a third example, a similar example. In a p-type semiconductor, the Fermi level lies 0.4 electron volt above valence band. If the concentration of accepted atoms, if the concentration of accepted atoms is tripled, find the new position. Find the new position of E of F. Please do it quickly. I'll take attendance till then. Okay, I'll take your attendance till you are solving this question. So we have number 2, 4, 6,
Present, sir.
8, 9, 11, we have 13, 15, we have 18, we have 20, we have 21, 4,
सर
25.
23 प्रेजेंट सर आपकी आवाज बहुत कम आ रही है।
You don't need to speak. I have a list in front of me. So we have 24, 5, 7, 6, 6, 8, 29, 30, 33, 4, 6, 38, 39, 40, 41, 44, 5, 48. Then you have 49, you have 53, 4, 5 and 6, 9, 62, 4, 6 and 7, 8, 9, 7, 1, 7, 5, 76. आसिफ का क्या रोल नंबर है 1726 का?
सर 78। थैंक यू सर।
ओके, ऑलराइट,
थैंक यू सर।
ठीक, ओके
सर
जी बताइए।
सर 33 की हो गई।
33 की होगी, जिसको जो लिस्ट में है उसकी हो गई। ऑलराइट, तो रोल नंबर 33 है।
यस सर।
बताइए व्हाट इज योर आंसर। जी बताओ, हैव यू सॉल्व्ड इट?
सर
रोल
सॉल्व
नंबर
कर रहा
30।
हूँ।
Okay, can you please open the camera and show me your copy? What are you solving? I will try to help you. Roll number 33. जरा अपनी नोटबुक दिखाओ, क्या सॉल्व कर रहे हो? 33. Can you hear me? Roll number 33. Okay. किसी ने सॉल्व किया ये?
यस सर।
Yes, sir.
What is the answer?
0.367 electron volt.
What is the next answer?
सर यही है 0.367 इलेक्ट्रॉन वोल्ट।
Okay, all right. I have calculated probably 0.3714, but I may be, मैंने शायद इसको approximate लिया है. Anyway,
सर
so this can be
0.379
0.37.
9
ओके, किसी और को 0.37 आया? EF minus EV that I have calculated, it is 0.3714. I don't know, but yours can be also correct. I don't know. शायद मैंने approximation मत की होगी. That can be also possible. चलिए next question करते हैं very quickly. We'll calculate the shift now. How much shift has been given to the Fermi energy level? Okay. So the question says like this. In a semiconductor at room temperature, the intrinsic carrier concentration and resistivity are 1.5 into 10 to the power 16 per meter cube. So this is intrinsic carrier concentration, and resistivity is 2 into 10 to the power 13 ohm meter. ठीक है, respectively. It is converted, then it says that the question says it is converted into an extrinsic semiconductor with a doping concentration of 10 to the power 20 per meter cube. Then the question says, it asks find the shift in the Fermi energy level. In the Fermi energy level due to doping. So what is given in this question? First of all, n of I is given. It is 2 into 10 to the power, sorry, it is 1.5. It is 1.5 into 10 to the power 16 per meter cube. Okay. Then sigma of I is also given. Sigma of I is also given. It is 2 into 10 to the power 13 ohm meter. Roll number 33, you have to show me copy after some time. Once I'll complete this. Then you have doping concentration, which is 10 to the power 20 per meter cube. So you have to calculate shift now. We know that shift is equal to kT. Then you have ln of nd by ni square. Nd by nc. It was basically nd by nc. So nc is equal to ni square. We'll write down like this, ni square. Please calculate the shift now. It is ni, not square. क्यों वहाँ पे ni हमने शायद ऊपर लिखा था, कहाँ लिखा था जब हम शिफ्ट कर रहे थे कैलकुलेट. Yes, it is ni. Okay. चलिए please calculate. Please calculate.
0.227 electron volt.
Yes, shift is equal to 0.227 electron volt. That is the correct answer. 0.227 electron volt. Okay. Similarly, I think we have done enough questions.